So I'll say first of all that we are related to some extent because his son, his youngest son, was my PhD student, and that son is today an assistant professor at the Technion, and as it so happens, the son of Paul Weiss, who was here this morning, I haven't seen him now, he was the presider this morning, his son is doing his postdoc with Yoav Shechman. So things are, all these circles and cycles are closed in a nice way. Danny is an example of, and I would quote Bernard Shaw, sometimes you have to call a spade a spade. Sometimes you have to fight for what you saw and what you believe in. And when you go into the lab, and sometimes the experiments do not follow common knowledge and do not follow theories, you have to check again and again and again. And if you are convinced you should that your data is true and is correct, you cannot look aside. You cannot say, okay, it doesn't conform with theories, therefore I will not publish it. You have to go out there and fight. And Danny had a major fight with no less than Linus Pauling. And the story about that area, I published a little bit in quasi-crystals, photonic quasi-crystals, but communities are now mixed in this. So the story goes that there were Danny and a couple of theoreticians, and that's it. And nobody else dared to stand against Linus Pauling until Linus Pauling passed away. And then within a year, everybody changed his opinion, his or her opinion. Everybody started to talk about the quasi-crystals. So this is how things are. And I think this is something that is, when Danny won the Nobel, and I can tell you the secret is that some of us thought that he should win it, and what we did is we didn't let go. You know, every one of us received this package from the Nobel Committee every other year. So what we did with it, we made sure that our friends at Weizmann or at Tel Aviv or Hebrew University will nominate in that other year. And there was a year, and this is something that Danny doesn't know, but I will say it now. I was trying to consolidate support from some major physicists because I nominated him for physics, and I went to Cohen Tanuji. Cohen Tanuji is the guru of quantum mechanics, Nobel Prize in Physics. So I had a serious discussion with Claude Cohen Tanuji, who happens to be a good friend of Israel, and I know him well. And he told me, look, physicists are an arrogant bunch. They will not give the Nobel Prize in Physics to someone that did not have any degree in physics. You have to nominate Danny for chemistry, and he will win. So after we understood that, we started to consolidate some senior chemists. Next year he won. So I don't know if he won because we nominated him. By the way, that year it was not from Technion. Chemistry people did not receive that envelope, so he was nominated from Weizmann. I don't know if you know that. Maybe there were other nominations, but from Israel I know for sure because we cooked it with some good friends in chemistry in Weizmann. So tonight he's going to talk to us, to deliver a semi-scientific talk about big mistakes. Not fraud, which also happens in science, but about big mistakes in science that have created a lot of noise in the community. And it's sometimes nice to reflect on them and learn from the mistakes.
Okay, fair enough. Thank you, Moti, for your short introduction, and thank you for making it short. I'll talk today about scientific blunders, and I will define what I mean by scientific blunders. This is my name, that's the way I spell it. Some people have other ideas. I'm from a Technion, I also have a position in Iowa State University. So, what is a scientific blunder? It must have something to do with bad science. So it has something to do with bad science, right. Now, the term pathological science was coined by Nobel laureate chemist Irving Nagmar in 1953 talk, and he characterized pathologic science as follows. Number one, the maximum effect that is observed is produced by a consecutive agent of barely detectable intensity, very small, faint intensity. Number two, the observations are near the threshold of visibility of the eyes. And as you'll see, in some cases, this is correct. There are claims of great accuracy. Fantastic theory contrary to experience. Criticisms are made by ad hoc excuses thought up on the spur of the moment, and the ratio of supporters to critics rise up to somewhere about 50% and then drops, and that's the end of that. So, a scientific blunder has to do with bad science. Okay, but that's not enough. That's not how I define scientific blunder. There are more ingredients in scientific blunder. Number one, a respectful scientist is involved. Not just a young man who is doing a mistake. No, a respectable scientist is involved. Number two, the media is involved. New York Times like media, big media. And I will skip this. I will start the first example by telling you about N-rays. Okay? So what are N-rays? We are now in Nancy, in France, and the year is 1903. And the title I gave it is Seeing is Believing. Background. The man, who is the hero of our story, is René Prosper Blondelot, who lived from 1849 to 1930, a respectful French scientist and a professor at the University of Nancy, who was the first to measure conduction velocity in wires, really a respectful scientist. The time is the beginning of the 20th century. Remember that X-rays were discovered in 1895 by Wilhelm Conrad Röntgen, a German scientist. In 1901, Max Planck announced the quantization of energy, and German science peaked, and its prestige soared, while the great French science of the past years is now stagnant. Nothing happens in France, and Germany is coming with new ideas and new discoveries. The media is deeply involved, and the new German discoveries and their implications were subject to public speculation and debate. This is the background. Now the story. In 1902, Blondelot was studying polarization of X-rays, looking forward to add his part to the growing body of knowledge. After the discovery of Röntgen, there were many people who studied X-rays, and he was one of them, and he did it in France. In one of his experiments, he was using a hot filament. I'll show you a picture how he did it. He was using a hot filament sealed in an iron tube that had an aluminum window. Blondelot noticed that something was happening in the laboratory when the filament was hot, when filament within the iron tube. The radiation that his apparatus emitted seemed to increase the luminosity of a nearby gas flame and to brighten screen coated with calcium sulfide. He has also noticed that a large number of materials emitted N-rays. So what are N-rays? Blondelot called his newly discovered emission N-rays, and N for Nancy. So we had X-rays, and now from Germany, now we have N-rays from France, and every French is happy. And in 1903, he wrote 10 papers on their properties of the N-rays. Other French scientists joined and added their contributions. For example, and these are very famous scientists, Becquerel wrote 10 papers on N-rays. Charpentier discovered N-rays emitted from human body. Zeeman conducted experiment and published. Broca published his results. Meanwhile, in Germany, the Kaiser invites Heinrich Rubin of the University of Berlin to demonstrate to him the new radiation. Rubens fails. He did not succeed in showing it to the Kaiser. 1904, this is a year later, Cambridge, England, a meeting of the British Association for the Advancement of Science, several European scientists discussed the N-ray phenomenon. Rubens tells his failing attempt. He said, I tried it, I could not do it. An American scientist, who is the hero of this story, his name is Robert W. Wood, from the Johns Hopkins University, not involved in European scientific power struggle, is chosen to go to Nancy and examine Blondelot experiment. They took a neutral person who didn't have any feelings toward Germany or France, and an objective observer, he was sent to look at the experiments as Blondelot was doing it. Wood reported his observations during his visit to Blondelot laboratory and detailed the info, he did it all the way. And he described several experiments he performed with Blondelot and his assistant, and the assistant is a key figure. None was convincing. In fact, Wood saw none of the effects that were claimed to be N-rays, and this is his Nature article on the subject. This short report by Wood killed the concept of N-rays. So what happened in the laboratory when Wood went there? So here was the experiment. So what you see here is the following. This is an iron tube. This is an aluminum window. This is the lens. And this is a flame. And this is the eye. And the eye is an eye of an assistant. Blondelot didn't see very well, so he hired an assistant. And the assistant said, it is brighter, it is dimmer, it is brighter, it is dimmer. This is it. This is supposedly the N-ray source. This is aluminum lens right here, spark, and ground glass, and the eye is that of the assistant. Okay, so Blondelot, because it is very dark there, Wood puts his hand on the way, and the assistant continued to say, brighter, dimmer, dimmer, brighter. This is experiment number 1. Experiment number 2. He wanted to show the spectrum of the N-rays. So here we have again iron tube, the aluminum window, and there's a beam. This is a slit, and the beam goes here. There's a prism here, and the prism supposedly is shining all the spectra in this. Now this is a calcium sulfide coated filament right here, and this is the eye of the assistant. So what the assistant does, he takes this wire and takes it up and down, okay, to measure the intensity of the supposedly spectra of the N-rays. And Wood is there, and the room is very dark, and he brings it up and down. He said brighter and dimmer and brighter and dimmer. It supposedly peaks, okay. And Blondelot sitting down and writing exactly the position and everything. At this point, Wood takes away the prism, grabs it, takes it away. And the assistant continues. Dim, bright, dim, bright, dim, bright. So Wood realizes this is all nonsense, writes his report to Nature, and this is the end of that. What is the epilogue? During 1903-1906, 300 scientific articles were published. 300 scientific articles by 100 scientists. Several scientists could repeat Blondelot experiment, most could not. These are the good guys. Among the reported properties of N-rays, because there were 300 papers, and some of them reported properties, most materials emit N-rays, including the human body. Wood does not emit N-rays, it absorbs them. N-rays enhance human vision, especially in dimly lit areas. Loud noise makes N-rays dissipate. Heat made N-rays more effective. What is the end? 1904, the French Academy of Sciences bestowed his Comet-Leconte Award on Blondelot because of his previous research. They forgot all of it. Everybody was blushing in the corner, and that was the end of that. Wood's debunking by his paper led to Blondelot madness, but he died many, many years later in 1930. Story number 2, some of you know this story, polywater. Now, polywater is really an interesting story because it has implications today. You may not know it, but it has implications today. And I'll tell you what they are. We are now in Kostroma, Russia, 1962, and I titled it, "This Borscht is Good for You." Discovery. A scientist, Nikolai Fedyakin, in the Technological Institute of Kostroma, was the first to observe that water sealed in glass capillary formed a second column separate from the first, and the new phase was found by Fedyakin to be denser than water, and the effect was called anomalous water. Fedyakin published his results in Colloid Journal. Enters Boris Deryagin. He is the key figure. Boris Deryagin died at the age of 92 in 1994. I met him before he died. He was the director of Surface Forces Laboratory in the Institute of Physical Chemistry in Moscow, respectable institute in Moscow during the time of communism. He had money, he had people, he had power. So, Deryagin, powerful and control of large, well-equipped group of scientists, takes over the research on anomalous water, and Fedyakin stays in the shade. He told him, "Go away, thank you very much. Now we will study this." And then there is an announcement. For several years, anomalous water was studied only in Russia. But in 1966, Deryagin was part of a discussion of the Faraday Society in Nottingham, England, and his talk marked the beginning of a long trail of studies in which prominent laboratories and eminent scientists around the world took part. In the United States, in Europe, the most respectable institutions and the most respectable scientists were part of polywater. Action. Between 1962 and 1966, Deryagin's group published 10 important papers in Russian. Deryagin designated an elegant apparatus to produce anomalous water in minute quantities, but much faster than Fedyakin. 25 scientists were working on the project in his group, and clean experiments were performed in quartz capillary tubes, not glass, quartz. This is important. Why quartz? Because quartz does not dissolve in water, and glass does. So quartz, clean water, capillaries, everything was fine. Reports on the strange properties of anomalous water started to appear in the Western scientific literature after the Nottingham meeting, in which I remind you, Deryagin declared about the polywater, and it was named then polywater in 1970. During the early 70s, about 100 papers appeared in the scientific literature every year. And here you see the number of papers that arrived as a function of the year. You see that it peaked and it came from different countries. It doesn't matter the details, but you see that it peaked and hundreds of papers were published. Deryagin claims that polywater was a stable form of liquid water, and that eventually all water will transform into polywater. So now there is a problem. Because when it reached the media, people started to say, "Hey guys, what are you doing there, scientists? Are you going to pour a little capillary into the ocean, and the ocean will turn into jelly, and that's the end of life on Earth? What are you doing there?" And this was in the public media and created a lot of problems. What are the properties of polywater as they were found? Boiling point above 160 C, and according to some reports, much higher. Freezing point below -30 C. Density 1.2 grams per centimeter, denser than water. Vapors of polywater condensed as regular water. The main idea, there is an order in liquid water, and the atomic structure and the atomic structure of the capillary surface determines the orientation of the water molecules well into the center of the capillary. Like a crystal is growing on the inside of the capillary. Polywater looked and behaved a bit like colorless syrup. Now the media. 1969. I quote a few journals. Miami scientific team creates, this is Miami Herald. Miami scientific team creates mysterious new form of water. This is from the chemical engineering. Discussions of practical applications today is considered bad form. Noted scholars have been cut dead for their colleagues for less than that. This is from the Newsweek. At least one research group is studying living cells for evidence of the strange new compound in them, in the living cells. And the scientists everywhere must be alert to the need for extreme caution in the disposal of polywater. Don't drop it into the ocean, they say. And in France, c'est eau qui ne sait pas, the water that never were. And Wall Street Journal, weird water, debate over mysterious fluid split scientific world. Polywater had bright future, or does it? Critics are charged it's only impure tap water. Chemical Week, can he prove it's water? And Washington Post, scientists growing wet, creepy water. And New Scientist throwing cold water on polywater. What is the end? In 1968, Deriagin had some 25 examples of polywater analyzed for purity. The analysis report claims that the amount of impurity particles in polywater matches the amount of water, 50-50. In short, polywater is a thick borscht of dissolved particles from the quartz tube in water. Now wait a minute. We said that quartz does not dissolve in water. This is true. But it dissolves very little. And when you have a very small volume and a very large surface in a capillary, then this tiny amount turns into a huge fraction of volume of the water. So, even if you put in very clean water, it becomes soup of silica particles in water. The analysis also claimed that the host of organic molecules were found in the soup, so it was not very clean. This marked the beginning of the end of polywater, and several years later, in 1975, there was no more activity in the field, as you saw before. Deriagin was then 73 years old, so was this the end of his career? Not so fast. And this is interesting. Several things happened. Because major universities in the United States and New York were involved with this fiasco, and hundreds of papers were published by eminent scientists, many institutes decided about peer review before you can send your paper for publication. When I wanted to send my paper to PRL, it was from NBS, it had to undergo peer review. All my papers had to go peer review. And I can tell you, I loved it. Because here are very good people, make comments that help me write a better paper, and their names do not have to appear on the paper. Wonderful, I loved it. So the committee came back and said the paper is fine, but is it not polywater again? We promised them that the scientific evidence are very solid, it's not polywater, and they allowed us, hesitating, but allowed us to publish the paper on the polycrystalline, on the quasi-periodic materials. Let's go back to the Deriagin. So by now, the Deriagin is not liked by anybody. In fact, he hated by everybody. I mean, everybody say, go away, Deriagin, don't talk to us anymore. And then Deriagin comes back several years later and says, hey guys, I can make diamonds from gas. Any gas that contains carbon, I will make you diamonds from this gas. Everybody said, Deriagin, go home. We had enough of you. But he was right. This time, he was right. And in 1976, Deriagin proposed a technique to make diamonds from the gas phase by CVD process, and it works. And all, the diamond story is very interesting. For many years, diamonds were sort of rare, and to produce artificial diamonds, you needed to go back to the original process that produced diamonds, which means high temperature and high pressure. That's how it is produced in the earth. So people developed techniques. GE had a company named Man-Made Diamonds, and they produce up to gem quality diamonds, and I have a story about that, but I'll spare you from that story, although it's very funny and interesting. And everybody said, wow, if we could make diamonds in quantities, diamond is an amazing material. It's the best heat conductor, 4 times better than copper. It's very hard, very stable, transparent to a large spectrum of radiation. Really an amazing material. Wow, if we could only have large quantities of diamond. And here we are, CVD diamond. If you want a plate like this made of diamond, no problem. We'll make a plate made of diamond, polycrystalline diamond. No problem. We can produce it in huge quantities now. And then it turns out there is not much you can do with diamonds. Not much. Yes, you can coat cutting tools with diamonds, but you cannot cut steels. You can cut aluminum only. Why not steels? Because the hot steel will steal the carbon, and the diamond will disappear. So it is used in the car industry to drill aluminum, and it works there. And a very few other applications. Really, really, the dream came true, and not much use to it. Now to the third story, and this is something that we lived in our time, it's cold fusion. If it sounds too good to be true, it probably is. Now, let's say a few words about cold fusion. Fusion is a nuclear process in which 2 light nuclei combine from a single heavier nucleus. Hydrogen fusion is the basis for hydrogen bomb, and possibly fusion reaction for controlled production of energy. This is the dream. Okay? This is the dream. Fusion reaction controlled to produce a lot of energy. In one such reaction, 2 hydrogen isotopes fuse from an isotope of helium, and here is a story. You take deuterium and tritium, and you fuse them together to produce helium, neutron, and energy. And energy is what's interesting. So people thought, wow, if we could have cold fusion, controlled cold fusion, maybe we could have it. But although this fusion occurs on all the stars, but it's very high temperature and very high pressure there, it's not feasible to use it to produce it in the laboratory in controlled manner. And although in a hydrogen bomb, Edward Teller was at the Technion once, and I came to listen to him. And he talked about the importance of education. Everybody was waiting for him to talk about, about nuclear weapons. And so at the end of the talk, one student raised his hand and he said, Dr. Teller, could you tell us how to make a hydrogen bomb? Oh, he said, that's very easy. Just give me an atom bomb and I'll show you. So what you have to do is the bang-bang thing. Okay, but that's besides the point. Fusion has been achieved by hydrogen bomb and under intense heat in controlled conditions, but only for a split of a second. Nothing continuous. Chemically assisted nuclear reaction at room temperature is therefore a dream worth pursuing. And it is because if it works, then it saves the world. On the 23rd of March 1989, Martin Fleischmann of Southampton University and Stanley Pons from the University of Utah announced to the media that they had developed a process for achieving cold nuclear fusion. The announcement was made in a press conference in the University of Utah a day before the article was sent to Nature. On the same day, on the next day, I should say, March 24, another paper was to be sent to Nature, that of Stephen Earl Jones of the neighboring Birmingham Young University, and the three had agreed to do so at the president of the two universities. So what was the agreement? they worked together. And I will not tell you why it happened, but they were neighboring universities. They worked together and they said, okay, we will announce it together. Nobody will have priority. The presidents of the two universities will be there. We will declare it to the public. But one university snapped, and instead of announcing it on the 24th, they announced it on the 23rd because they wanted to be number one, and they paid for it. However, the University of Utah team snapped and made the announcement a day earlier. What led them to do that? So here's the chain of events. 1984, Fleischmann takes an earlier retirement from the University of Southampton and goes to visit his former student and co-researcher, Pons. So Pons was a student of Fleischmann. Both of them are excellent scientists, by the way. They discussed the possibility of creating cold fusion by an electrochemical process and decide to go for it, in secret. The experiment continued till 1988, for 4 years in secret. 1986, Johnson Palmer begins similar experiment in Brigham Young University, a nearby university. The team eventually builds a new neutron detector, which is good. 1988, Fleischmann and Pons submit research proposal to Department of Energy and to send a proposal, and they send a proposal for review to Johns. Johns realizes that, hey, in the next university they are working on the same thing. He realizes that his neighbor work on the same subject and proposes, I must say, rightly so, coordination of effort. They agree and involve the university management. So the presidents knew about it. The announcement created a huge wave of enthusiasm in the science community and in the media, and for a good reason, because if indeed they had such process, it could have improved the life of every person around the world. Imagine, cheap electricity means unlimited amount of distilled water, food available everywhere, cheap chemicals, metals, transportation. Hey, energy, abundance of energy. So the dream was huge. And all this without exotic heavy metals like uranium, like in nuclear reactors, no radioactive elements produced as in fission reaction, no fancy, expensive equipment, simple, abundant elements like hydrogen will do the trick, just clean, pure, cheap energy, and everybody was happy at the prospects. So here is the experiment that they had, and I must make a little introduction. Palladium has been known to absorb hydrogen in large quantities. So the idea was that if hydrogen is absorbed, it will create enormous pressure inside the palladium, so much so that here and there the process will start. This was the idea. And it has been known that by electric power you can do miracles, right? You can separate the hydrogen from oxygen in water. Try to do it any other way. And with electricity you do it just like that. So they said, hey, that should be interesting, let's do it. So this is a cold fuel gel. I called it a genie in the jar. The FP power unit was small, portable, cheap, and very simple. The fusion reaction was to be achieved by electrochemical process in solution of lithium and heavy water, deuterium oxide. Palladium electrons was loaded with hydrogen, and after several hours, so they say, started to produce heat and neutrons. They claimed that they observed heat up to, from room temperature to 50 degrees centigrade, and they say they detected neutrons, which is a clear sign of a reaction going on. So what we see here, this is very simple. This is palladium cathode, this is palladium anode, heavy water and all these ingredients inside, a stirrer, and that's it, and a plus-minus connection to a direct current. That was simple enough. Fleischmann and Pons insisted that the process produced energy as heat, neutrons, tritium, and helium exactly according to the equation. They claim that it works. A clear indication of cold nuclear reaction, cold fusion. Experiments to reproduce these results started immediately all over the world after the announcement. Some announced success. However, most failed. People did control experiment. Very few succeeded. More and more evidence appeared in the press that have explained why the process could not yield the reported results and the program faded. Thermodynamically, it's impossible. The media was deeply involved. The disappointment matched the initial expectations. Because the expectations were so high, the disappointment was just as high as that. What's the end? January 1, 1991, Pons resigned from the University of Utah and went to work in France, by the way. The president of the university resigned before him. However, research on cold fusion continued around the world after that. A good number of studies were sponsored by governments. Governments said, hey, okay, we can spend the $100,000 for a chance of being wow. So it's okay. So in many countries, they continue research, and it didn't work. Fleischmann and Pons continued their effort in the field, but in France. So, was cold fusion a scientific blunder? Yes, it was bad science. They were respectable scientists. The media was involved. These are my definitions, so it matches. But is it a scientific blunder? Probably yes. It doesn't work. It will not work the way they wanted. But the expectations were unbelievably high, and rightly so. What's the epilogue? For the next 17 years, efforts, this is our time, effort to duplicate the effects had mixed successes, and panels organized by the United States Department of Energy, the first in 1989 and the second in 2004, failed to find convincing evidence that useful source of energy would result. However, low-level research continued, and claims of experimental success were reported primarily in non-mainstream publication. It's a dream. Doesn't work. Now, in 2006, Moiser Boss and Spack, researchers in the United States Navy Space and Naval Warfare Systems Center in San Diego, developed a new experimental technique, a key feature in which the electroplating of probes to set ratio of palladium to deuterium, certain ratio. They continuously coated to create the desired pressure. These experiments were produced, these have produced evidence of high energy nucleation reaction concentrated near the probe surface. Based on this work, two other teams were reported similar findings at the American Physical Society meeting in 2007, although interpretations vary. And this is the end of the story. It doesn't work, it doesn't work, it doesn't work. And here is my last slide, old caricature of the 17th century of an alchemist's laboratory. Look at the master, his helper, cooking something, and look at the ladies hiding in the corner. Thank you very much.
Thank you, Danny. I think, well, Shaul wants to ask a question, so.
No, I want to tell a story. First of all, thank you for the beautiful talk. I have a story about Robert Wood.
Oh, yeah.
There was a there was a heavy winter in Philadelphia, and the train tracks frozen. There was ice, and they could not operate the train, so they called him as a consultant. And he wanted a large fee, which they agreed to pay. And then he said, well, no problem. He took the electric wires from the train, put them on the tracks, and then the ice melted. So then they said, oh, it's so easy. we are not going to pay you what we promised. He said, if you don't, I will reverse the wires and the ice will come back.
Yeah. So actually, Robert Wood was actually a real inventor. He invented many things in optics, and there's a major award for his name. Any other interesting stories from the audience, or maybe questions to Danny?